Let's take a look now at Chebyshev's theorem, named after this fellow here. Here's what Chebyshev's theorem tells us, right? It's going to be a measure of dispersion. So what we want to know is how's the data compacted around the mean? So first of all, suppose we have a set of data having mean x bar and standard deviation s, right? So you have a bunch of data values, compute the mean and standard deviation. Now here's the first thing it says. It says at least, okay, this is important here. It doesn't say exactly, but it says at least this percent of the data will lie within k standard deviations of the mean. Now here's what k is. So you've got this formula here. I'll write it up here. 1 minus 1 over k squared percent. Now what is this k? All right, that's what this is down here. All right, so k is the number of standard deviations from the mean. I'm going to draw a picture of this in just a minute. All right, so here's what we know. At least 1 minus 1 over k squared percent of the data will lie within k standard deviations of the mean. And the second thing it says is at most 1 over k squared percent of the data will lie farther than k standard deviations of the mean. We don't have to worry too much about the second part. I just wrote it so the theorem's complete. But really, here's what we want to know. Here's what this theorem tells us. At least this percent of the data will lie within k standard deviations of the mean. So let's interpret this. I'm going to do it by notation, and then I'll draw some pictures. All right, so first of all, suppose that S is some sample standard deviation, right? You've got a collection of data, you compute the mean, you compute the standard deviation, and we're going to call the standard deviation S. Now, just as a matter of notation, if you write 1S, all right, that is 1 standard deviation, right? That represents 1 standard deviation. If you write 2S, this is 2 standard deviations. If you write 3S, that is 3 standard deviations. Now, this is just like what you did in algebra with x. If you had just an x, that's 1x. If you have 2x, that means you have 2x, 2 times x. X appears twice, 2 times. If you have 3x, it means x appears 3 times, or 3 x's. ... What if you had this? Ks, all right? That is k standard deviations. All right, this is why I wanted to do this, because we're going to use this. We're going to use this here in our notation when we interpret it. And I just wanted to be sure you know what it means. So that multiplier out there, that just tells you how many standard deviations you have. If it's a 5, you got 5 of standard deviations. 3, you got 3 standard deviations. 2, you got 2. So just in general, k can be some number. And it just tells you how many standard deviations you are from the mean. All right, so what this is going to say is this. The first one, I could write x bar plus 1s. This is 1 standard deviation from the mean. 1 standard deviation from the mean. If we write this one, x bar plus 2s, that is 2 standard deviations from the mean. ... If I write this, x bar plus ks, that represents k standard deviations from the mean. All right, so a bunch of notation here, just so we know what it says, is this. All right, what if we wrote this? X bar plus 7s. Oh, that's not, I don't want to write 7s. X bar plus 3s. What does that represent? This is 3 standard deviations from the mean. All right, so x bar is the mean. You add, what you're adding is this number of standard deviations. let's be sure we got this. You know, I think a picture is going to help. So let me get some room over here, and we'll draw a couple of pictures, just so we're sure that we understand this notation, because it'll help make sense out of the theorem when we write it. Okay, what if we had this? All right, so how about first of all, let's suppose I'm going to draw a number line here. Got x's on this line. Here's x bar. Okay, there's the mean, sample mean. Now, suppose that we're over here, x bar plus ks, x bar minus ks. So do you see what's happening here? You're at the mean, and then you go over, like, whatever k is. Suppose k is 3. You go over 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left. I'm going to draw another picture in just a minute. All right, so what I'm doing now is this. I've got a theorem. I want to interpret the theorem, so I need some notation. Now, I come down here and I want to interpret this. You know, I just saw this. 3. Come on, Denny, there's an R in there. All right, so what we're saying is that in here, in that interval, how much of the data is inside there? Well, what we're saying is this. The amount of data is 1 minus 1 over k squared percent. Let's not do one for number 2. We're really not going to use the second part. Okay, so what I'm saying is that if I come over, pick some standard deviations, 4. If I come over 4 standard deviations to the right, 4 standard deviations to the left, how much data do I have in there? I'm going to have 1 minus 1 over 4 squared percent. Let's actually do this for some numbers. All right, first of all, look at what happens if k is equal to 1. Well, if k is equal to 1, the theorem doesn't work, because here's the theorem, 1 minus 1 over k squared percent. And if k is equal to 1, right, if k is equal to 1, what have we got here? We've got 1 minus 1 over 1 squared, which is 1 minus 1 over 1, which is 1 minus 1, which is 0%. So it says none of the data is in that interval. Right, so we don't use k equals 1. K has to be greater than 1 for this theorem to apply. So now, what happens if k is equal to 3? We'll do a couple of these. If k equals 3, then 1 minus 1 over 3 squared, 1 minus 1 over 9. Now 1 minus 1/9 is 8/9. And I've seen this one before, so I know that that's 0.89, and that's 89%. All right, so that says 89% of the data, of all your values, will lie within 3 standard deviations of the mean. All right, so if we draw a picture here, all right, here's the mean, x bar, x bar. If we go over 1, 2, 3 standard deviations to the right, 1, 2, 3 to the left, how much of the data, right, all your data, how much is in here? Well, we don't know for sure, but we do know that it is at least 89%. Okay, let's do one more, actually. I'll do it up here at the top. What if k is equal to 4? All right, then, actually, let's do it this way. 1 minus 1 over k squared is equal to what? 1 minus 1 over 4 squared equals, can you finish it? Once you try to finish it, maybe put this thing on pause for a second, come back, and then I'll go ahead and finish it for you. Make sure we all get the same answer. Let's see if we all get the same number here. 1 minus 1 over 16. All right, 1 minus 1/16 is 15/16. And 15/16, I'm running out of room. I'm just going to say 94%. Okay, it's not exactly, but it's close enough. So 94% of the data lies within 4 standard deviations of the mean. You can almost read this. All right, so get a good feel about what's happening now. For any set of data, if you go out, I'll do it down here. If you go out 2 standard deviations, you've got what? At least 75% of the data. If you go 3 standard deviations, you've got at least, what did we say, 89%. You've got almost all of it. Just go out 3 standard deviations. At 4 standard deviations, you're way up there at least 94%. Okay, and remember, it's at least. All right, so by the time you're out to 2 standard deviations, you've got 3/4 of the data. 3 standard deviations, you've got essentially 90% of all your values. Let's look at an actual numerical example. Suppose that for a set of data, suppose we've got, say, 33 pieces of data, and we make a computation. We get x bar is equal to 77.58. All right, so the mean of these 33 pieces of data is 77.58, and the standard deviation is 7.15. Okay, now, let's just pick a number for k. Suppose it's 2. If k is equal to 2, then we get what? It's going to be, here's what I want to compute, right? I want to compute 2 standard deviations. So 2s is going to be 2 times 7.15, and that turns out to be 14.30. All right, so 2 standard deviations is 14.30 units. Now, here's a picture. Here's the mean at 77.58. Now, if you come out 1 standard deviation, maybe you're here, and 2 standard deviations, you're here. So what number is this? This is going to be, all right, the mean, all right, this is x bar plus 2s. So this is going to be 77.58 plus 2 of those standard deviations, 14.30. So we're out here at 91.88. That makes sense? You know, if you're following your data, you're out here at 77.58, and you add 2 standard deviations. So to the 77.58, you add 2 of those 715s, you're at 91.88. Now, if you go the other way, there's 1 standard deviation, there's 2. So this is going to be x bar minus 2s. So it's going to be 77.58 minus that 14.30. And my calculator shows that is 63.20. So let's interpret this. We know at least, right, don't forget those words, at least. Now, what are we over? We're 2 standard deviations away, right? Over here, we said k is equal to 2. And at 2, we were what? At 89%? No. At 2, we were what? At 2, we were 75%, for Pete's sakes. Okay, so here's what we know. At least 75% of all the data values are within, okay, let's say this. Well, at least 75% of all the data values lie between, how about BTW? Between 63.20 and 91.88. So a picture is going to look like this. Here's our mean, 77.58. And if I come over here to 63.20 and over here to 91.88, what I know is that, okay, I've got data in here. Oh, you can't see that. I've got data in here. And there's some out here, you know. But how much have we got in here? We have at least 75% of the data is in this interval right here. All right, that's Chebyshev's theorem.